Hi, I'm Randy Nesse from the Arizona State University Center for Evolutionary Medicine. Our guest today is Paul Griffiths. Paul's a philosopher from the University of Sydney who actually is deep into biology, and especially evolutionary biology, and especially the evolutionary biology of disease. Paul, how did you ever get interested as a philosopher in biology and medicine?
Okay. Well, I'm a philosopher of science, which is a kind of separate field within philosophy. And as you know, philosophers have always been fascinated with the mind. And there I was a grad student, I was trying to work on the nature of mind, and I realized I was never going to understand anything about the mind unless I understood its biology. And when I started looking into the philosophical problems that are raised by biology, there was more than enough there to keep me going for the rest of my career.
Sounds like a similar path to mine. I'm finally practicing as a psychiatrist and realizing I really have to know not just how the mind works, but why it is the way it is before I'm going to make sense of mental disorders. Mm-hmm. So where did you take it from there?
So I've always been really interested in understanding development. There's a long tradition in philosophy. I mean, we don't think of philosophy this way these days, but a lot of Aristotle's work was how do animals grow? What is growth?
From a single cell to...
Whereas he would have thought, not even from an egg. Aristotle could see that birds grew from eggs, but he didn't think mammals came from eggs, or reptiles. He didn't know about that. So actually maybe he knew about some reptiles because of snake eggs, that he's in Greece. But there are a lot of things that come from eggs that he didn't know about. And then Kant, Immanuel Kant, one of the greatest philosophers in history. Mm-hmm. Again, we don't think about Kant this way, but half of one of Kant's three major works is about how to understand living systems, the distinctive nature of human knowledge when we try to understand living systems. And in some sense, that's still what we're doing. We're trying to understand how science works and what big lessons science teaches us about the world. And one really interesting area to ask those questions is the biological sciences. So the biological sciences are very distinctive. They don't have, a few, there are some exceptions, but in general, biologists don't discover universal, beautiful laws expressed in a simple piece of mathematics. Mm-hmm. They describe very complex, unique things that just happened once in the history of the universe.
So you'd say there's kind of a fundamental difference between understanding biological systems and physics?
There are some bits of biology that are like physics. Theoretical population genetics is a science comparable in many ways to physics. But molecular biology, developmental biology, and particularly evolutionary biology in terms of the actual history of individual species, and ecology, I often think, ecology is probably closer to economics than it is to physics. It's a science, really, it's the economics of non-human organisms. So very different.
We can only spend a minute on this, but they talk about laws of economics. Mm-hmm. Are those like the laws of physics or fundamentally different?
Fundamentally different. In fact, as great American philosopher Elliot Sobers argued, a lot of the things that we call laws are, well, they're true because they're a bit of maths, but they're not true in the way that we think of scientific laws are not true because the maths makes them true. They're true because we collect a lot of observations and the world makes them true. But a lot of what we do in economics and in biology is to take something which is just true by definition, it's a beautiful piece of mathematics, and then do really clever and useful things with it. And we can call those laws if we want, but they're not like discovering that the value of the gravitational constant, right? You don't have to go and measure a bunch of things.
So let's go on in a minute. I'd like to hear what you think about how we can tell what's disease from what's normal.